In this problem, we have the opportunity to relate rotational power to torque and rotational speed for a motor or a shaft that you might find in an electromechanical or purely mechanical system. So in the notes, we have relationships for power, mechanical power, electrical power. And when it's mechanical, you have either the opportunity to look at rotational power or linear power. For this case, we're going to use the equation for rotational mechanical power. And that equation is that the power is equal to the torque times the angular velocity. And we can rewrite this, since this problem is asking how fast is a motor spinning in units of radians per second, as the power divided by torque. So what is the power? The torque, the power is 5 horsepower, and the torque is 17 Newton meters. Now, it's often helpful to write out some of the standard units that we find when using any of our equations, but this equation in particular. This angular velocity, with the way it's written out in terms of watts and Newton meters, is given in units of radians per second. So that's a little bit different than, say, revolutions. Well, it's a lot different than units of revolutions per minute, or even a pure frequency, like how many rotations per second. Okay, so this is something that you want to keep in mind whenever you're using this rotational mechanical power, or the formula for rotational mechanical power. Now, it's also probably helpful to remember or to refresh ourselves in terms of what 1 horsepower is equal to, because watts, that's going to be in our metric system, and horsepower would be kind of more of an imperial unit of power. Okay, so about 746, 750 watts, whatever, is equal to 1 horsepower. Now, when we do the math for this kind of simple formula, we just have omega is equal to 5 horsepower, but we convert it over, okay, so using dimensional analysis, and you can watch the organic chemistry tutor if you want a little bit of information on dimensional analysis, or there are other videos as well, and here we're talking about it, but we are trying to keep track of these dimensions. So you see horsepower here, horsepower here. This will then give us watts in the numerator, which is what we have here, and then we have the torque, which was given to us very nicely in metric units of Newton meters. So that's the equation there, and we run it out, and we get our result in radians per second. Okay? Now, how do we go about doing this in Colab? So let's go back to our browser here, okay, and we can go ahead. Oh, that's an old one, so I guess I'll come back here, and we'll call this something like shaft power. Okay, so shaft power. And once again, we do import numpy as MP, and I'll go ahead and run that and create a new cell like that. And this is not that crazy of a formula, but in this case, we have power given to us, and it's, so we'll say P. All right, and we'll say that that was 5 horsepower, and it's often convenient to go ahead and convert at the very beginning. People have different ways of doing this, but just to keep things straight, so I'm going to do 5 times 745.7, okay, watts per horsepower is going to give me units in terms of watts, all right, W. And the equation uses torque. So the torque that I was given was 17 Newton meters. Again, these are just comments, and to keep the unit straight as we do our calculations. And then we write the formula, which was that power is, omega is equal to power divided by not time, torque, okay? And I'm going to say that's in units of radians per second. And we go ahead and we do print, okay? And we're going to say, okay, omega is equal to omega, we'll say 1 decimal point, 1 decimal place. And here we'll do radians per second, just like that. Okay, and we run that. And yes, we got 219 radians per second, which is what we had last time. So this is a fairly straightforward way to calculate or the relationships between power, torque, and angular velocity with P equals torque times omega. Thank you.